For generations, NASA spacecraft have captivated our imagination. But how do scientists decide what projects to pursue? And how are the probes and craft designed in the first place? We visited the Compass Engineering Lab at NASA's Glenn Research Center to learn more.
This is a laboratory. We don't really mix chemicals or fire off rockets here, but we create new spacecrafts here, new concepts. So we have a laboratory environment because we have different people from different areas working together to what we call concurrently engineer a spacecraft design.
So how is this model for designing spacecraft perhaps different than how it was traditionally done 10 or 20 years ago?
In the past, you would usually meet once a week. You would say, I have a requirement for a power system for my science payload of 100 watts. Next week, the power person would come off and design, a solar array to provide that. You come back next week, and guess what? The scientist has changed his mind. I really want 200 watts. So now this poor power person has to go back and change it again. So usually a design cycle would take 3 to 6 months for a conceptual design like this. Well, with this concept here, with people all together at one time, you can eliminate those problems. You can work together to come up with new innovative designs and do it in 2 weeks instead of 6 months.
So it certainly saves a lot of time and then presumably a lot of cost as well.
That's correct.
So once that design leaves this space, what do you do with it then?
So once it leaves this space, we'll do a complete design. We'll do all the pieces, parts of the spacecraft. We'll do a configurations you've seen. We'll also cost it out, and the cost will go forward to the project managers, and they'll say, do I want to go forward with this or not? If they decide yes, they'll go to another level down in engineering detail. They'll also start to bring in other team members from other agencies, from commercial people, to start getting more meat in the bones, if you will, and to start going forward with the process. They're actually looking at something now like that to go out and capture an asteroid. So something we developed here a year ago. They're going to the next step and saying, this is really what we want to do. So,
how do you determine what projects to do or to mock up? Can people just bring their own ideas, or do you have sort of a set schedule of things that people are interested in looking at?
We are here for any projects that need us. In fact, that's the real key, is that we have this talent, we have these people here to provide this capability, so before they even go off and spend money on it, they can have us do it quickly, and they can say, this is something worthwhile, we'll do.
So what are some of the past projects this team has been involved in?
So we worked quite a bit on constellation. We did different lunar landers for the piloted missions. We did upper stages for that. We've done quite a few things for the technologies here at Glenn Research Center. Other centers like JPL and Goddard have their own conceptual design teams. They work mainly on things that are new missions to different planets. What we do here is the same kind of missions, but we're looking at new technology here from NASA Glenn. We specialize here in communications, power, and propulsion technologies, as well as really intense environments, so high temperature environments like Venus. So we're usually taking those components and integrating them with spacecraft to saying, hey, now that we can enable this mission. We did one recently to go to Venus, to actually put a land sailor on Venus, and we actually had electronics that actually survive the very high temperatures of Venus. So taking those things and really enabling that. So.
Some of these projects I would suppose have very unique challenges, like Venus, which has very high surface temperatures as well as very high pressure. How do you work together as a team to meet those challenges? What's the process of what that looks like?
So the process is very basic. We really need to have a primary investigator. So someone who comes in, whether it's a scientist or someone with a new technology, and bring them in and say, what do you want to achieve with this? What are your figures of merit? You know, what are your requirements? But they'll actually sit here at the middle table and they'll work with all the team here. And as we go through the design, they'll say, I want to do this much science, bring this much data. And then the realities begin to hit. Then the people say, well, if you want to do that, you'll need a Saturn V launch vehicle. We can't do that. So a little give and take begin to happen. Sometimes we come up with new ideas where they can actually do more than they thought they could do, what they can expect. So we'll work through with the team as we work through the design and come up with these ideas. And by the end of the 2 weeks, the primary investigator is really integrated with the team. But we'll go around the room to all the different subsystems. We have thermal, structural, propulsion, etc. Each one of those will have their subsystem, and they'll be really integrated. So The propulsion person will say, I need a thruster, a rocket that runs this much thrust. The structural person says, well, you're going to need this much structure to handle that. So it all is integrated together very quickly. You come up with a design that would actually work.
So what are some projects that you're working on now?
Right now, as I said before, we were working on the asteroid capture, doing quite a few things for different technology offices, looking at radioisotope power systems. Right now, we're actually working on quite a few things for the SCAN project, which is the communications group here, looking at what's the next steps for relaying information back and forth. Quite a few new things are looking at different higher frequency ranges to provide more data rates. Also looking at lasers, using lasers to return information from Mars. That's a new challenge. Galileo and whatnot would be able to transmit through the atmosphere to big dishes down in Australia and whatnot. Lasers have problems when you have clouds. So do you actually have a relay satellite to capture the laser, then use a different frequency down? All those type of trades and different kind of vehicles get traded through concepts here.
This process of collaborative engineering isn't necessarily new, but it's sort of expanding in its uses. What are the future directions you see this type of engineering going?
Usually there's a whole stack of documents you have to do when you build a spacecraft. Interface control documents, requirement documents, whatnot. What the people in the project are trying to do now is get away from that and just have a model. So you imagine a computer model that actually has attributes of size, mass, power, whatnot. It's all in the model. It's not in a document anymore. You know, a lot what we do now is model-based engineering. We do have a master equipment list with masses and powers, but we do have a model. But let me emphasize that it's not a spreadsheet. It's not a computer program coming up with these ideas. It's the people. The bottom line is I want people who know space and who can use this tool here. So,
could you maybe expand a little bit on how you would like to see this process used more and maybe move into other areas of what you guys do here at Glenn?
We've actually started moving into balloons. NASA has a lot of balloons that fly telescopes, other scientific equipment. Again, these are items that have been flown for years, but using the conceptual design process, you can quickly do the payloads. We'd like to start working into aircraft. We've done aircraft, say, on Venus before and Titan, but going back to aircraft in the good old Earth here, we can apply these design processes there too. So really, if you have the right people, the concurrent engineering process does work for conceptual design. So.
What kind of engineers do you like to bring into the fold? As you've talked about, I mean, you have a lot of, I would imagine you need a lot of creativity, a lot of very specific skill sets. What type of people and engineers do you look for to be part of a team like this?
Well, this is a hard one. Can you guys all leave when I say it? Really need people who are creative. Listeners are very important. There's so many good ideas coming around here, and it's really surprising. A lot of times the good ideas will come from, in propulsion will come from maybe the communications person. Right, Joe? I shouldn't do that. But that sometimes it'll actually happen. So, but obviously you have extroverts and introverts. And the way we set have our design processes here, we are working together live, so we'll work a whole afternoon together. So the extroverted people are very happy with that. The introverted people would like to go back to their desk and work, so we have the mornings available for them to do that. So, but the real nice thing is once people get comfortable with the process, they begin to cross over and get comfortable working the other way. So we have a ton of fun. We have a YouTube Friday. We usually watch a video of some rocket launch or something else to have a little fun here. So we really enjoy ourselves. So.
At this point, I'd like to see if you can maybe walk us through the project you're working on now, or maybe some of the projects you've done in the recent past.
So they'd like to send a crew past the low Earth orbit, past space station, and they need to find a place for them to go that's scientifically valuable. Asteroids came up right away. Asteroids pass by the Earth fairly closely often, so it'd be nice to have a crew of astronauts go out, scientists go out and look at these asteroids. It turns out that the vehicles, and we've designed the vehicles to do that too, are fairly large. They're almost as large as a space station to get you pushed out to this asteroid and come back. It's also very risky for the astronauts to go that far away. When the astronauts went to the moon, it would only take 4 days to get back if they had a problem, Apollo 13. If you go out this far, you'll take a year to get back. So if you really have a lot of problems, that's a long time to wait if you have an abort scenario. So they asked us to look at, can you capture the asteroid and bring it back to high Earth orbit? In other words, instead of taking Muhammad to the mountain, bring the mountain to Muhammad. It first sounded crazy to us too, but it turns out if you have something roughly the size of 10 meters, 1,000,000 kilograms, You can actually capture it with a large inflation bag device. You would grab around the asteroid after you despun, or after you match the spin rate, grab the asteroid, then you would despin the asteroid, then you would just kind of nudge it back. We're talking about very small velocity changes for a near-Earth asteroid. Something that's in a similar orbit to Earth but passes by every once in a while. You do the bit nudging back and capture in a high lunar orbit. From there, the astronauts can go out to the moon, as they're used to doing. If they have a problem, they can come back in 4 days, and they can explore the asteroid right there. That kind of system would take about 6 tons of xenon propellant using electric thrusters, about 40 kilowatts of solar arrays, and it would take about 6 years to push that back. Roughly $1 to $2 billion for that robotic vehicle, but much cheaper than sending a crew into deep space. So that was of great interest to the manned program right now, to give them that target to go to.
Is that a project that you could see actually coming to fruition and moving to the next stages?
It's a very outlandish concept, if you would. But Wall Street was very interested in it at first, and there's actually a Dilbert cartoon that talks about the concept, basically saying, can you go off and find these asteroids? Because Wall Street would like to mine them, because they're full of titanium, platinum, things like that, iridium. So a lot of precious metals are on these asteroids, and it should be great to grab them and bring them back so you can mine them. So.
Do you have any sense of what percentage of the concepts that get drawn up in this type of setting actually make it to being physically constructed?
Right. We hope that they would all make it, but obviously they don't. There's not enough money for that. We do about 12 to 16 concepts a year, and you can imagine there's not that many NASA spacecraft launches a year. So what we've done now, we've had about 2 launch. We've been around for about 6 years, so we had 2 concepts launch. A lot more would have been launched, but the Constellation program was kind of put on hold. But when they launched the Orion spacecraft, the heavy launch vehicle, we did designs for all those things, so those will be launched fairly soon. So, but some of the concepts don't come out. I mean, they just don't. They don't show a lot of promise. They cost too much. They don't bring back enough science return, and that's fine. That's why we do what we do. It's a very low amount of money to work out the thing right now and say, this is not worth doing, instead of spending a lot of money on something that is going to be worthless anyways.
So can you tell us a little bit about the Venus project that you guys worked on?
The NIAC, which is innovative proposals from NASA, they look at very outlandish things, even more so than the asteroid. We had a person here, Dr. Jeff Landis, who is actually a science fiction writer. He's a Nebula Award winner, writes a lot of short stories and novels. And he came up with an idea to not just land on Venus, but to put a land sailor on Venus. Venus has a fairly dense atmosphere. It's about 90 bar, which is about 90 times what it is Earth here. But it's very hot. It's about 800 degrees Fahrenheit, so like your oven on clean cycle. So it's hard to make, say, you take your computer or take a little robot and try to put it in your oven, it would melt very quickly. So here at Glenn Research Center, we have silicon carbide technologies, which is basically providing a computer chip built on a different substrate that actually would survive those temperatures. So, but not only are we going to land on Venus and take data, but since there is this wind blowing, or wind or current, depending how you look at it, the thought was we could put on a land sailor. So you would take basically a sail or an airfoil. When the wind is blowing, you could use that just like they do out in the desert to push this vehicle back and forth. So you would slowly creep along and explore different parts of Venus from this vehicle. So that's very exciting, because I mean, having motors on there requires a lot of power, whereas this thing, the sail actually doubled as a solar array. There's a little bit of light coming into Venus, and so you'd have just enough power to run the motors to run the sails. So it wouldn't require a lot of energy. So it was very exciting to do that.
Can you tell us a little bit about the project you all are working on today?
So today we're looking at next generation of relay for spacecraft. Now NASA has what they call the TDRS spacecraft constellation up there now. Basically it provides a relay for low Earth orbiting spacecraft, anywhere from a small robotic spacecraft up to space shuttle launch vehicles, as well as space stations. So it provides that relay. If you only use the ground, you'd only be able to talk to the ground as you flew over 10 minutes or so. And you'd have to have ground stations all over the Earth. It's much easier to have 3 spacecraft in geostationary orbit, which is the same place you get your television programs from, and do it in that method. we need to go to the next step. How do you do it more efficiently? How do you do it better? Obviously, in the past we had dedicated spacecraft, so today we're looking at a new concept called hosted payloads. Those same television satellites we talked about actually have room on board them. So can we take parts of the TETRAS spacecraft, put it on board this geostationary spacecraft? So now it's providing you with television, but it's also tracking our robotic spacecraft and bringing back data. It could be a great way to save money for NASA, so we can spend money on some of these other ideas to go into deep space. So that's basically what we're doing today.
The collaborative environment at the Compass Lab allows scientists and engineers to work quickly and efficiently to design the next generation of exploration systems. To learn more about NASA research and the exploration of the universe, visit redOrbit.com.